All right, guys, so the last thing we're going to talk about is essentially nucleophilic substitution reactions and elimination reactions. Okay, so before I even get into it, let's define the word nucleophile. So if we break down this word nucleophilic, nucleophile, phile meaning love and nucleo meaning positive. So a nucleophile is something that likes positive charges. All right, something that likes things that are positive. They like it in a nucleophile again because the nucleus is positive. When we start Orgo 2, we'll start with electrophilic, or we'll talk about electrophilic reactions. Electrophiles, therefore, love negatives and are usually positive charge. To be a good nucleophile, you need a lone pair of electrons or a fully blown negative charge on your nucleophile. So nucleophile, again, means loving positive charges. Now, we're going to talk about something called alkyl halides. Alkyl halides are sp3 carbons that one of the carbons is bonded to a halogen. A halogen's notation is usually the letter X, and you'll see it with the multiple Lewis dot electrons, lone electrons around it. The key about a Lewis structure of an alkyl halide, for that matter, or the bonding, is that there is a dipole moment that moves this way from carbon. The halogen is important because the halogen ends up with a partial negative charge on it, while my carbon ends up having a partial positive charge on it. Okay, so a partial negative and a partial positive charge on it. All right, now there are three types of alkyl halides. Okay, I mean, we could throw methyl in there where they're all halogens, but we really focus on these three over here: primary, secondary, and tertiary. And what that means is the following: how many carbons are attached to the carbon that has the halogen. Now, R is a shorthand for carbon chain. Okay, it could be one carbon, it could be 100 carbons. It just means that there is a carbon there. Okay. And at one point, I will be better writing with a mouse. So a primary, all right, is a carbon that has the halogen attached, is bonded to one carbon. A secondary is going to have two carbons attached to the carbon with the halogen, and a tertiary is going to have all three. So I have to be an sp3 to be an alkyl halide. Okay. I have to have at least one halogen attached. And then I'm classified by how many carbons are attached to the carbon that has the halogen functional group. Okay. So again, like I said, it's a dipole-dipole interaction. It's a polar between the two molecules, but they are polar due to the difference in electronegativity between carbon and the halogen, where the carbon is going to get a partially positive charge and the halogen is going to get a partial negative charge. Now, why is this important? Well, this is important because of what we just talked about the definition of a nucleophile. A nucleophile is going to look for positives. So my nucleophile, which is sometimes represented by Nu with a negative or Nu with two dots or whatever, is going to love this positive. Okay, it's going to be attracted to that positive, and we're going to talk about doing substitution reactions where this bond breaks, taking the electrons with the halogen, and the nucleophile, whatever the new negative charge thing is, comes in and bonds to the carbon. But without that dipole-dipole interaction to make carbon positively charged or even partially positive charged, this reaction won't happen. So the first thing starts with the difference in electronegativity between a carbon and the halogen functional group. To name these, we'd call it chloral, whatever, chloromethane, chloroethane, all right, and so on. And this is just showing the general structure of the difference in the electrons around the bigger atom. So iodine's bigger, so you're going to see a bigger negative. Bromine a little bit bigger or a little bit smaller. Then chlorine smaller, and then fluorine even smaller. To be 100% honest, these are the two, if we're ever going to use the halogens in a lab, it's always usually a chloral or bromine because they're the ones most controlled. But in theory, this could apply to all three. It's just which gives us the better results, or all four, I should say. Okay, so again, nucleophile seeks nucleus. It's looking for a plus charge. Lewis bases, electron donors, are our best nucleophiles. When we make the new bond, the nucleophile is giving both of its electrons. We are making something called, again, a coordinate covalent bond. Okay, a coordinate covalent bond is going to form because it's not going to be equal electrons. What's really going to happen is the following. These are going to go with the halogen. These are going to make the new bond with the carbon. Now, I want to show you this or point this out. Electrons always follow the arrow. You always draw an arrow from where the electrons are to where they're going. Okay, so carbon isn't attacking the nucleophile. The nucleophile is attacking carbon. We're not going to worry right now about elimination. That's the second part, okay, where we actually eliminate a bond and change our geometry. We're going to focus on the top hand. We're going to focus on the substitution reaction. They're called nucleophilic substitution reactions, and they are usually abbreviated SN1 because there's two types, and SN2, and we will talk about both types. All right. So, how is this going to work? All right. Well, the nucleophile is going to look to attack a positive charge entity on there. They can attack the protons that are on carbons. They can attack the carbon itself, and that's how we're going to look at all these different reactions. Okay. Now, another factor that plays a role, okay, in essentially having this reaction occur. So, we've got a rule, all right? Let's take some rules down that we're going to look for. Number one rule is that you have essentially a polar covalent bond. For these to occur, you need a polar covalent bond. Okay, it's usually the alkyl halide type. A carbon bonded to a halogen, all right, where there's the partial positive charge being formed and a partial negative. Okay. 2. Is my alkyl halide is it a primary, secondary, or tertiary? Because that's going to determine how we do our reaction. 3rd, what is our nucleophile? Is it a good one? An okay one? A bad one? And we'll talk about that. 4th, what is our leaving group? God, I love a new fresh marker. Sad when you get to that age and that point in your career that a fresh marker for a whiteboard makes you giddy. Leaving group. What's the one that's going to break away? Okay. sometimes shorthanded Lg, like so. What is my leaving group? Is it a good leaving group? Is it a bad leaving group? Okay, the worse the leaving group, the harder the substitution reaction. So again, what's going to happen? Okay, that I showed you on the slides. The nucleophile is somehow going, these are going to go with that, the halogen, and the nucleophile is somehow going to bond here with this carbon. We have to take into account how this is going to happen, that number one, we do have this bond. Number two, is it a primary, secondary, tertiary? Number three, how good is my nucleophile? Number four, how good is my leaving group? The better my leaving group, the better the reaction will go without any extra assistance. Okay. So, here's some rules about that. If we go left to right across a row of periodic table, all right, of the periodic table, our basicity decreases. So, the less basic I am, the better I am as a leaving group. Or you could say it, the more acidic I am. But they really don't talk acidic, all right? Organic chemists talk basicity all the time because they're talking about the movement of electrons. So the further I am to the left on a periodic table, the worse I am as a leaving group. So I have the choice of ammonia or water. The oxygen as a leaving group or ammonia. Oxygen's going to be better because it's further to the right. Fluorine's going to be better because it's further to the right. Carbon's going to be terrible because carbon's further to the left. So a carbon-to-carbon bond is not going to be a good leaving group. Okay, basicity also decreases down a group. And this was all Gen Chem stuff. Okay. So the weaker I am as a base, the better the leaving group I am. Fluorine is going to be worse leaving group than chlorine. Chlorine than bromine, and bromine than iodine. Iodine reacts so fast it's hard to control, so it's a great leaving group, but we usually don't use iodine. Fluorine's a terrible leaving group, and it has to do with size. Think about it. Fluorine is being attracted to the nucleus, and there's not much electron shielding. So does fluorine really want to go? No, fluorine is set. But as I get bigger and bigger as I move down a group, my basicity decreases. Okay? And therefore, it's easier for that leaving group to leave because there's electron shielding there that's not attracting me to the nucleus of carbon. So, again, better leaving group as I go across left to right on a periodic table, and then down a group. Okay? So the further I am down in a group, the better I am as a leaving group. The further I am to the right, the better I am, if we're comparing periods. Okay. All right, and here they show you the math of the leaving group. Here's my pKa. I'm going to be a huge base because I have a very high pKa, which means I have a low Ka, which means I'm basic. Okay. So again, what's my leaving group going to be? Good leaving groups, like I said, look at their pKa's. Very low numbers, which means they have high Ka numbers, which means they're acidic. Okay. All right. So let's take a look at the general features of a nucleophilic reaction. All right, an SN reaction here. To bring my nucleophile to the party, whatever my nucleophile is going to be, I usually have some group 1 ion to bring it to said party. Okay. So if I'm going to have an ion as a nucleophile, it's probably going to be either a salt or a strong base. It's going to be an ionic compound that brings the nucleophile. So what they're saying here is, I want to add a hydroxide to an alkyl halide. Okay. So let's do that. Well, how do we get the hydroxide into the reaction? Well, add some sodium hydroxide. But what about the sodium? Well, sodium's going to be there to balance the leaving group, the bromine. But I'm going to be 100% honest. Organic chemists don't care about this. I had a student all last semester and the semester before, all through Orgo 1 and 2. They wanted to balance the Orgo equations. They wanted to be able to balance things. They needed to see it all. I need to see it. And I had to get them out of that mentality because organic chemists really don't care until they're producing products what the balanced equation is. They don't care about the inorganic stuff over here. That just balances itself out due to the law of conservation of mass. But has no relevance on the organic compound that's formed. So we bring the nucleophile in, the hydroxide. We have our leaving group, bromine, which is a good one. The nucleophile attaches, and the bromine is gone. How does that happen? We'll talk about it. And look what we've done. We've turned, one bromopropane into one propanol. We've taken an alkyl halide and we've turned it into an alcohol. If I use a neutral nucleophile, as they show down here, my product will end up having a positive charge. And here we took our alkyl halide and turned it into an amine. Okay. So those are our plans here. So what makes a good nucleophile? What's going to have us be a good nucleophile? If I am a strong base, the stronger I am as a base, the better I am as a nucleophile. So what they're saying in step 1 is this. I have OH minus versus acetate. The nucleophile in both is that tail oxygen. What I would do is look at the pKa values. 15.7 for H2O. Okay, which means a low Ka value. CH3COH is 4.8, which would have a higher Ka value. Or if you remember, the higher the pKa value, the more basic I am. So OH is the stronger base. And another way to look at it is, how much is let's say we're comparing oxygens. What is oxygen in a tug of war against? A hydrogen versus a carbon. Well, oxygen is going to be able to pull those electrons closer to it, be more electrophilic, therefore be a stronger base. Number 2, a full-blown negative charge will always be better than the conjugate acid. F minus will always be a better nucleophile than HF. OH minus will always be a better nucleophile than H2O. And number 3, what if I don't have a comparison? I'm not a conjugate and I don't have the same in charge. The more basic I am, the better I am as a nucleophile. So it's the exact opposite of a leaving group. Okay. Leaving group is better if it's more acidic. Nucleophile is better if it's more basic. So if my nucleophile, my leaving group gets better as I move to the right across a period, my nucleophile gets better as I move to the left. So carbon is a horrible leaving group, but it's a great nucleophile compared to nitrogen, compared to oxygen, compared to fluorine. Okay. And I know after taking my first exam, you could already see how the questions may formulate in our exam. Okay. So let's go back to our board now. And at our next thing that will determine our reaction. And on our board, is number 5. And number 5 is, what solvent are we in? Our solvent that we're doing the reaction in. okay, will also determine the process of how we're going to do our substitution. So here are our solvents. We have polar protic. Okay. Polar protic solvents. Okay, has a hydrogen in there, bonded to some strong electronegative atom. So HCl, H2O, HBr, something like that can form hydrogen bonds. And if we're looking at just specifically hydrogen bonds, we could even cut out HF and HCl in the halogen and focus specifically on water and nitrogen, because to make a hydrogen bond, you have to be, well, we can keep fluorine in there, but it's usually water. All right, polar protic solvent. Okay, polar protic solvents are great for dissolving cations and anions, which would get our nucleophile into the reaction. Our aprotic solvents that don't have that ability to make hydrogen bonding, it doesn't do too well with anions. Our polar protic solvents are more suitable for SN1 reactions. So star that, mark that down. Okay. And aprotic solvents, those without hydrogen, are better off for SN2. And we'll talk about the differences. Protic solvents, methanol, ethanol, butanol, acetic acid. Things that have a hydrogen bonded to an oxygen. That's what we're looking for. Whoops. That was a terrible circle there. Here, here, and of course, wow, my mouse is all over the place today. And right there with water. Okay. The mouse pads start moving all over the place here. Okay. Aprotic solvents, they don't have that hydrogen ability to bond. They could still be polar aprotic. I'm polar, I have a charge, but I don't have that proton. Acetone, acetonitrile, those are the two you see the most, especially those of you who are going to go on and use HPLC and do stuff like that. Yes, under supervision and things like that, you may use THF and DMSO. Okay. Those are some polar aprotic solvents. So, what could give you keys at which way your reaction is going? Number one, the first key is, do I have a polar covalent bond? Then, am I a primary, secondary, or tertiary alkyl halide? Then, what is my nucleophile? Then, what is my leaving group? Then, you can also look at the solvent. And in a chemical reaction, okay, let's say we have an organic compound bonded to X. The solvent will usually be put over the arrow. So that'll be a key too. And on the worksheets on Blackboard with this, those are your keys. Okay? Those are some keys to essentially getting the correct answer of which process you're going to go by. Okay? This is just showing what happens in protic and aprotic solvents. Okay, we talked about how good the nucleophile is and why, okay, it's important. All right? Another one that plays a role in your nucleophile is steric hindrance. If the nucleophile is bulky, even though it might be a better base, it might be a better nucleophile, it might work better. If it's bulky, that is a no factor. Steric hindrance is going to bother our reaction. All right. So here's the general mechanism that's going to happen. The sigma bond between the halogen and the carbon chain is broken. The nucleophile gets in there. Now the question is this. What happens when? Does this leave and then this attach? Does this attach and this leave? So there's two types. There's the one-step and the two-step. Okay. SN1 is two-step. SN2 is one-step. The reason being is the 2 and the 1 come from second order or first order. So back to your chemical kinetics. Okay. So let's look at the two ways these can happen. And we're just going to look at the carbon. We're not going to look at the rest of this. We're just going to look at the carbon and look at the steps. All right. If I am a carbon bonded to my halogen, the one step works like this. Okay, this is the SN2 mechanism. Now, mechanisms are not chemical reactions. They are, but they go into deep detail. Okay, they go into huge detail about where the electrons are coming, where the electrons are going. So, let's say I've got a primary alkyl halide. This is going to be SN2. It's going to happen in one step, meaning bimolecular. And the reason it's bimolecular is the concentration of my alkyl halide and the concentration of the nucleophile both play a role. Here is the mechanism. The electrons attack the carbon with the halogen, and this bond starts to break. There is no set, stable intermediate, but if we were to break this down, here's what we would be seeing. Okay? Nucleophile here, carbon there, the bond breaking with the halogen, and my hydrogens all around. It would then yield the following. Carbon bonded to hydrogen, bonded to hydrogen, bonded to hydrogen with the nucleophile. And this is important. Mark it down. The nucleophile. And we'll do this over here. We'll have plus, if you need it there, your X minus leaving group. The nucleophile in an SN2 is on the opposite side of where the leaving group was. It has to be. The way I see these is kind of like Newton's cradle. You got a ball here, a ball there, and this ball comes in, hits that one, and when it does, knocks that other ball off. Okay, that's the SN2 mechanism. Two steps, because if I increase either one of these, I'm going to get more collisions. Therefore, this reaction is going to happen faster, all based on the kinetics. SN1. Okay. Two steps. All right. I have my, and I'm going to use a tertiary. You'll see why in a little bit. Okay. I'm going to have a tertiary. I have my leaving group. And I have my nucleophile sitting here waiting. Step one is my leaving group leaves. I have to present it in a situation to make that leaving group want to leave. We'll talk about that. So my leaving group leaves. I do create a stable intermediate. My stable intermediate is a carbocation. The nucleophile now loves the carbocation and comes in. Now the reason it's SN1 and only unimolecular is I could keep dumping nucleophile in at time 0, but my nucleophile can't do anything until that leaving group leaves. Okay? Our products. Since I have an open situation here, my nucleophile can actually attach to either side because it's not being forced to come in, bump, and what is known as the backside attack. Okay. So in an SN2, backside attack, simultaneously addition and removal. In an SN1, leaving group has to leave, nucleophile then comes in. And of course, if you want, there's of course that sitting over here as possibly one of your products. Okay. Questions so far? Anything? Or are we okay? Okay, so we talked about the mechanism. So here's where you should start taking maybe a graph, some notes, something, an SN1 side and an SN2. SN2, one step. Okay, my best bet for an SN2 reaction to occur is right here if I'm a methyl or if I'm a primary. As soon as I become a secondary or a tertiary, my rate goes down significantly and tertiaries are almost zero. And the question is, well, why? Well, if we think about it here, I'm a nucleophile. So right away, here's your hint. Do I go SN1? Do I go SN2 in my mechanism? Look at your alkyl halide. Back to our list. Look at your alkyl halide. If I'm a nucleophile, I've got an easy way in there. Very small hydrogens, easy to do the backside attack. If I try to get in here, the steric hindrance is so great, it's a giant blocker for that nucleophile to get in there and knock that bromine off. So SN2 reactions are very good with primary and methyl halides. Which means that what? SN1 are going to be good for these and are right for secondaries. Okay. So there's our transition state like I showed you guys. Okay. And again, you get a rotation, so it ends up on the other side. Make sure if you have to draw a mechanism or anything like that, and you do SN2, that you draw the reverse geometry. Okay. So again, factors affecting it. I need a decent leaving group. I need a really good nucleophile since I'm attacking right away. I need something that's a strong base. I need something with a negative charge. I need a really good nucleophile to get in there and attack. My leaving group it doesn't have to be the greatest leaving group because the attack of the nucleophile is going to knock it off in an SN2. Okay, and look at all the SN2 reactions you could do and the products you can create. This is going to be, for those of you who are taking me for Orgo 2 in a week, essentially, going to be very important. I'm going to expect that you know, hey, I could do this reaction and get this and that and the other when we start building on things. Okay. So how about SN1 reactions? All right, so here's our influence. The substrate, all right, primary is the best, or methyl. My nucleophile needs to be good. My leaving group can be just okay. And I really, an aprotic solvent will be all right. I don't need a protic solvent. I don't need ions to form. Maybe for my nucleophile. But for the most part, I should be all right there. Okay. Key this, backside attack, inversion of the chemistry, like I said. Okay. How about SN1, two-steppers? What are going to be good for the two steps? Secondary and really our tertiary alkyl halides. Okay, I already showed you the mechanism, but it's there again. Look at that. Look at that reaction rate for SN1 reactions for tertiary. You have a tertiary, you are going SN1. Hands down, no doubt, got it. Okay. The first step of the reaction is slow to get that leaving group. So how do I get that leaving group to go? I need a solvent. I need something with a strong negative charge. Something that's there to dissociate. Something that could protonate. I need a protic solvent. I need that proton on there to essentially get this double bond. If we're looking at the rates, the slow rate is essentially getting our carbocation to form. We have a faster rate. Okay. Once the carbocation forms and the nucleophile is free to attack. Okay. The mechanism is there, showing what's going on. All right. So let's look at why also, besides steric hindrance, that SN1 is likes tertiary and secondaries more than primaries. And what it has to do with is carbocation stability. Okay? So, we have a reaction. And I have a choice. So I take my primary alkyl halide and I turn it into a primary carbocation. I have a secondary alkyl halide. We'll do this primary. I have a secondary alkyl halide. Okay. And I turn it into a carbocation. I have a tertiary alkyl halide, and I turn it into a carbocation. Okay. There's no bond. By stability-wise, most stable, least stable. So if I were to do an SN1 reaction and form a carbocation with a primary, the carbocation would be terribly unstable. Now the question is, well, why is a tertiary more stable than this right here, a primary? Well, what you got to understand is carbon is kind of a little whore. Carbon will leave you in a second for something better. Now the thing about that is, so why wasn't carbon staying with the halogen? Why doesn't carbon want to be with the halogen? So I always bring up the meme where it's the guy walking with the girl and he's looking at the other girl. All right, that we all know that meme. That's carbon. Carbon's in a perfect relationship with this halogen, but another sexier, better nucleophile in carbon's mind comes along and catches carbon's eye, and carbon's like, you're out of here. Now, as a partying gift, the halogen gets to take the electrons. Okay? So now, carbon's dumped the halogen and becomes positively charged. That positive charge can get distributed throughout all the carbons. The more carbons I have, the more resonance I have, the more stable I am. The more carbons I have, the more that positive charge can be moved or absorb some of the pain, all right, from breaking up of carbon, all right, to those other carbons. So this is the most stable. And I once said that about carbon, and the one girl in my class said, oh, I dated a carbon back in high school. And I was like, I think we all know a carbon from either side of the table there. or you've been a carbon before. All right, but to each their own. I'm not here to judge. Okay, so the more carbons I have around to spread that positive charge around that central carbon, that carbon that had the leaving group, the carbocation, the more stable I am. So this is why tertiary carbons love to undergo SN2 reactions in one, or SN1 reactions in 2 steps, and the alkyl halides. So steric hindrance does play a role, but also the formation and stability of said carbocation. Okay. All right, and this is all mentioned in the slides. All right. Nothing about carbon being a whore, but you know. Okay. What type of solvent? I'd like to be an aprotic solvent. Okay, so here's our comparison, our summary of SN1 and SN2 reactions. Okay, and the differences and the reaction rates. And it is here again. All right. Now, one thing I do want to point out, and I'm going to point it out here, the solvent, as we talked about, is here too. Polar aprotic solvents for SN2, 1 steps, because we don't need to get that leaving group to protonize. Okay. But I do, and again, I have multiple times that we talk about this. All right. So I'm going to, there's one thing I do want to point out. I'm going to stop that. All right. And about this carbocation business. And this will kind of catapult us, and we'll talk about elimination on Tuesday. And that'll finish up, and all this substitution elimination will be on the final. Okay, so your next exam is all stoichiometry. Sorry, I'm thinking my Gen Chem course. Will be all stereochemistry. It started with an S. I'm not that far off. But I want to show you something here. Let's say I had okay. Carbon like that, and here was our halogen leaving group. Okay, so let's say I have a secondary a secondary alkyl halide, all right, or something like that, and I'm going to do a reaction. No, you know what? Let's do it this way. I'll do it both ways, but I'll do it this way first. Let's do it this way. I've got this. Okay. Yeah, and let's put one here like so. And I'll do it this way first, because this way will make more sense, I guess, at first. Okay, and let's say this is my halogen. So I have a secondary alkyl halide. Okay, and I have a good nucleophile and all of that, but we know, and I'm in my protic solvent, so we'll say we're in water. We have a good nucleophile. We don't need a great one, not like an SN1 reaction. Or sorry, SN2 reaction, 1 step. All right, so our halogen leaves. Okay. And we left with a carbocation that looks like the following. Here's my carbocation. Here's my my other carbons that are here. And we have something that looks like that. So we would think that, okay, now the nucleophile will come in here and will form that product. So we'll have, whatever it is, 2-methyl-3-nucleophilo-butane. Okay, whatever the nucleophile is, bromo, chloro, whatever it is. The truth of the matter is this doesn't happen right away. This is a secondary carbocation. However, if I were on this carbon, I'd be a tertiary and I'd be more stable. So here's what happens. It's known as a hydride shift And what could happen is this hydrogen comes in here like so. We get our carbocation now on here, because now it's a tertiary. That hydrogen that moved is now here, so this hydrogen is this hydrogen. And now my nucleophile attacks there, and instead of having, let's say this was 2 bromo, 2 methyl, 3 bromo, it's now 2 methyl 2 bromo. Okay? Now, the same thing can happen if this was a CH3, and we would call that a methyl shift. Now, it can only happen if the carbon's next door. It really doesn't happen if it's 4 carbons down. But after, and this is what I tell students all the time, after you create the carbocation, see to the left and right, can you make a more stable carbocation? Can you go from a secondary to a tertiary by moving a hydrogen or a methyl group over? If you can, do it before you add the nucleophile. It's called a hydride shift or a methyl shift. Okay, so this stuff is in substitution reactions, and elimination reactions are in. I had it open and then I dropped the book. I believe it's chapter 6. Yep, chapter 6 is nucleophilic reactions. You can try the homework in there, the sample problems. And like I said, there's some up on Blackboard. And then chapter 7 is going to be elimination reactions, which we are going to attack on Tuesday before your final on Thursday. And by final, I mean your last exam. So that's that.